Good morning, students. Today we'll see the concept of microstate and macrostate. First of all, we see macrostate. Consider four distinguishable particles and we wish to distribute them into two exactly similar compartments. In an open box, let the particle be A, B, C and D. When any particle thrown into the box must fall into one of the two compartments are alike. The particle have the came a priori probability of going into either of them and will be the half. The possible way in which four particles can be distributed into two compartments as shown in the table. In this table, there are two compartments and the number of particles in the compartment. When we throw the particle into the compartment, one of them will fall in the first compartment and other will fall in the second compartment. Similarly, if we suppose in the first throw all particle will fall in the compartment 2 and no particle will fall in the compartment 1. In second throw, one particle will fall into the compartment first and 3 particles will fall into the compartment 3. In the third throw, 2 particles will fall in the compartment first and 2 particles will fall into the compartment second. Similarly, in fourth throw, 3 particles will fall into the first compartment and 1 particle will fall into the second compartment. And last, in the fifth throw, all 4 particles will fall into the first compartment and no particle will fall into the second compartment. In this way, there is a distribution of the particles. Thus, there are 5 different distributions such as 0, 4, 1, 3, 2, 2, 3, 1, 4, 1. Each compartment-wise distribution of a system of particles which is known as the macrostate. In general, for a system of n particles to be distributed in two similar compartments, the various macrostates are 0n, 1, n minus 1, 2, n minus 2 and n minus 1, 1 and lastly n 0. Therefore, the total number of macrostates are n, particle is n plus 1. Now we will see the microstates. In the microstates, possible arrangement and number of microstates, that is denoted by W. Microstate 04 in first compartment 0 and in the second compartment ABCD, its probability is 1. Microstate 13 in first compartment ABCD and in second compartment BCD, CDS, DAB, ABC and the probability is 4. In this way, the distribution of the particle is shown in this table. And the last, that is you will see the last, that is 4. In the first compartment, all 4 particle is there, that is ABCD, and in second compartment is 0. Its probability is 1. In this way, this is the distribution of the microstates. Since the particles are distinguishable, the number of different possible arrangements in each compartment is shown above. Each distinct arrangement is known as the microstate of the system. In the above exercise of 4 particles, the total number of microstates are 16, that is 2 raised to 4. Suppose we consider a thermodynamic system of n identical non-interacting particles occupying a volume V. Let E1, E2, E3 and En be the energies of the particles, and N1, N2, N3 and Ni respectively of the particles. Total number of energy, total number of system E equals to N1 E1 plus N2 E2 plus N3 E3 plus so on plus Ni Ei, that is equals to summation of Ni Ei. The possible values of energy of each particle are discrete, and hence the total energy E at GE so has discrete values, but when the volume V is very large, there is a large number of different ways in which the individual E1 can be chosen so as to make total energy equal to E. Thus, the actual value of parameter N, V and E defines a particular macrostate NVE of the given system. Each of the different ways in which the total energy of the system can be distributed among the particles constituting it species a microstate. Thus, a given macrostate corresponds to too many microstates, and it is very natural to assume that at any time the system is equally likely to be in any of these microstates.